Hi class, welcome to this new video, still on Laplace transform, but our focus is on the unit step function. An important function in modeling many physical situations is a unit step function, as shown in the following graph. I have one, u, t equals to a, it's an empty circle, and I have a field circle like this. So t is equal to a excluded, this is 0, and this is 1. And this is a graph of the unit step function ut minus a. Therefore, defining a unit step function, we will say that a unit step function ut minus a, where a is a given number, is defined as ut minus a equals to 0 if t is less than a, and 1 if t is superior or equal to a. So this can easily be visualized on the graph, right? When t is less than a equal to 0, that's what you have here. When t is less than a, you have 0 is on the x-axis. When t is superior or equal to a, you have 1. Okay, now let's have a look on some practical example, student, and graph example. Graph ut minus 5 and ut. Okay, this should be a very easy exercise for you to solve. Just using the definition of a unit step function, you can easily graph those by, let's graph the first function, the first unit step function, right? Let's say I have 2, I have 4, I have 6, so here is 5. So I'll put an empty circle here, and this is 1. So using the definition here, I will have that u t minus 5 equals to 0 if t is less than 5, and 1 if t is superior or equal to 5, right? So 0 if t is less than 5, so if this t equal to 5, I have an empty circle because 5 is not included. T is strictly inferior to 5, so 0 on the x-axis, and then 1 if t is superior to 5, so this is 1. Now, if I have to graph the second unit step function ut, what happens is that having that ut can also be written as ut minus 0, right, equals to 0 if t less than 0, and 1 if t superior or equal to 0. And how do we graph this? Is easier, right? I have my graph here, and then I have 0, so I have 1 here. So when t is less than 0, I have 0, empty circle, 0, and when t is superior or equal to 0, I have 1. So that is the graph of my unit step function ut. Now, one of the means why the unit step function is very useful is that the unit step function helps us to properly write piecewise continuous function in such a way that the Laplace transform can easily be determined. Let's consider the function f of t equals to ut minus a minus ut minus b, having that a and b are two numbers where b is superior to a. So if t is less than a, what do we have? If t is less than a, we have that f of t equals to, according to the definition, if t less than a, it's 0, and by default this also will be 0 because b greater than a, 0, 0. If t right? If a is less than t, less or equal to t, and equals to b, I have that f of t equals to 1. According to the definition here, is 1 minus 0 equals to 1. And if t superior or equal to b, what I have also here by default, I'll have that t is superior to b, by default also superior to a. So ut is 1, and ut minus a is 1, and ut minus b also is 1. So I have 1 minus 1, which is 0. So this function can be written. So this function f of t can be also written as 0 if t is less than a, 1 if a is less or equal to t less than b, and 0 if t superior or equal to b. So we can see that we're able to easily rewrite the piecewise continuous function in terms of unit step function that help us to easily find their Laplace transform. So in the next video, we will see together how we will be able to determine the Laplace transform of unit step function. Thank you very much for paying attention to this video. See you soon. Thank you.